Welcome everyone. I am Dr.R.Mathammal, Associate Professor, PG and Research Department of Physics, Sri Sarda College for Women, Salem. Before start my lecture, I would like to say quotes on elementary particles. We are all connected to each other biologically, to the earth chemically, and to the rest of the universe atomically. The exploration of the elementary particles is one of the pinnacles of human curiosity and ingenuity. Now we are going to discuss about various topics of elementary particles. First one, introduction to elementary particles. Then a brief history of elementary particles on the basis of characteristics of elementary particles such as mass, angular momentum, spin, time. The elementary particles can be classified into 4 groups. Then every particle has an antiparticle. Similarly, every matter has an antimatter. Then various forces among the elementary particle can undergo various types of fundamental interaction among the elementary particle. The last one is conservation laws and symmetry. Elementary particles are the fundamental building blocks of matter and energy. They are indivisible entities that cannot be broken down further into smaller components. The subatomic or elementary particles form a long list. These particles are elementary in their nature and they are structureless. They cannot be explained as a system of other elementary particles. Why we study the elementary particles? The study of elementary particle is driven by a desire to understand the fundamental nature of reality, explore the origins of the universe, advance scientific knowledge and technology. Next we discuss brief history of elementary particles. The history of elementary particle is a fascinating journey through the evolution of our understanding of the fundamental constituents of the universe. The concept of the atom was an indivisible particle was first proposed by ancient Greek Democritus. In the late 19th century, J.J. Thomson discovered the electron through his experiments with cathode rays. Rutherford's gold foil experiments in 1909 revealed that atoms have a dense positively charged nucleus leading to the nuclear model of the atom. In the early 20th century, the experiments by Rutherford and Chadwick and others led to the discovery of proton and neutron as constituents of atomic nuclei. The development of quantum mechanics in the early 20th century laid the foundation for understanding the behavior of elementary particles at the atomic level. The standard model of the particle physics developed in the later half of the 20th century provides a comprehensive framework for understanding elementary particles and their interactions. Scientists continue to search for new particles and phenomena beyond the standard model, exploring ideas such as supersymmetry, extra dimension, and dark matter. The brief history highlights the remarkable progress made in our understanding of elementary particle from ancient to research of today. Now we discuss characteristic properties of elementary particles. Elementary particle possesses characteristic properties that define the behavior and interactions. Some of the characteristic properties of elementary particles are mass, electric charge, spin, quantum numbers, lifetime, color charge, interaction. Elementary particles have mass, although the masses vary widely among different particles. For example, electrons have a much smaller mass than protons and neutrons. Many elementary particles carry electric charge which can be positive, negative or neutral. Elementary particles have intrinsic angular momentum known as spin. Spin can have integer values, that is 0, 1, 2 or etc. for bosons, or half integer values half or 3 by 2 for fermions. Elementary particles are characterized by various quantum numbers such as lepton number, baryon number, isospin, etc. Describe the properties and interactions of particles and play a crucial role in particle physics. Lifetime. Some elementary particles such as electrons, quarks are stable and have infinite lifetimes. Color charge. Quarks possess a property called color charge, which is analogous to electric charge but associated with strong nuclear force. Elementary particles interact with each other through fundamental forces such as gravity, electromagnetism, weak nuclear force, and strong nuclear force. The nature and strength of the interaction depend on the properties of the particles involved. These are essential for constructing theoretical models and predicting the outcomes of the particle physics experiments. Understanding these characteristic properties of elementary particles such as mass, intrinsic angular momentum, and the nature of the reaction, the elementary particles can be classified into 4 different groups, namely the protons, baryons, leptons, and hadrons. Baryons. Proton and particles heavier than proton form this group. Proton and neutron are called nucleons and the rest are called hyperons. Every baryon has an antiparticle. If a number called the baryon number +1 is assigned to baryon and the number -1 is assigned to antibaryons. In any closed system, interaction or decay, the baryon number does not change. This is the law of conservation of baryons. Hyperon is a special class of baryons characterized by time decay of the order of 10⁻⁻10 seconds. Mass value intermediate between those of neutron and deuteron. The decay time is very much greater than the time of the formation. It is because of this unsolved problem these particles along with K mesons are called strange particles. There are 4 types of hyperons, namely lambda, sigma, cascade and omega hyperons. Leptons are weakly interacting particles. Charged leptons also show electromagnetic interaction. There are 12 leptons, electrons, positrons, pair of muons and 3 neutrinos. Leptons appear to have no internal structure and are point particles. Electrons, the first elementary particle discovered, are negatively charged, stable, having rest mass 9.11 into 10⁻⁻31 kg and rest energy 0.511 million electron volt by c square. It is a fermions, that is electron has spin off. Positron is an antiparticle of electron. hence is called positive electron. Muons were first observed in cosmic radiation and have a mass of 200 times mass of the electron. Muons are also spin-off particles. Tauons have comparatively recently been discovered having a large mass heavier than nucleons. They are unstable and decay into muons and two neutrinos. Muons are first discovered during beta emission, and the other neutrinos were obtained in other nuclear reactions. All neutrinos are stable and having zero charge, spin off, and negligible mass. All the leptons interact weakly with other particles. The fourth type of elementary particle is meson. Mesons are strongly interactive and include pions, kaons, and eta mesons. And all mesons are having masses between that of a pion and a nucleon. And two more mesons are added to the list. These are charmed mesons and beautiful mesons, which are heavier than nucleons. Pions that can exist as positively and negatively charged and neutral particles have zero spin and are responsible for short-range nuclear force. Kaons are produced due to interaction of high-energy particle at very short range due to strong nuclear force. Eta mesons exist as neutral particle which has a very short lifetime. Among the various mesons, kaons are strange particle, but the rest are not strange. The neutral pion and neutral eta mesons decay by electromagnetic interactions, while the rest undergo weak decay. All mesons have zero spin and odd parity and are bosons. Next we discuss particles and antiparticles. In particle physics, for every elementary particle, there exists a corresponding antiparticle. Antiparticles have the same mass as the corresponding particle, but opposite electric charge and quantum numbers. When a particle and its antiparticle meet, they can annihilate each other, producing energy in the form of photon. Here are some examples of particles and their corresponding antiparticles. Electron. Electron is a negatively charged lepton. The antiparticle of electron is positron with the same mass but a positive charge. The proton is a positively charged baryon. The antiparticle of proton is antiproton, which has same mass but a negative charge. Neutron is a neutral baryon. The antiparticle of neutron is antineutron with the same mass but opposite quantum numbers. The muon is a negatively charged lepton. Antiparticle of muon is antimuon with the same mass but a positive charge. Neutrinos come in three flavors: electron neutrino, muon neutrino, and tau neutrino. Each flavor of neutrino has its corresponding antineutrino. Next we discuss matter and antimatter. These are the two complementary forms of particles and opposite electric charges and other quantum numbers. When matter and antimatter come into contact, they annihilate each other, converting their mass into energy according to Einstein mass-energy relation equal to mc square. For example, an hydrogen atom composed of one electron and proton. The antimatter of hydrogen is antihydrogen, which is made up of a positron and an antiproton. Antihydrogen would have a spectrum similar to that of a ordinary hydrogen. Indeed, from a collection of antiproton, antineutron, and positron, a word of antimatter must be constructed, which could be indistinguishable. To understand the significance of existence of large number of elementary particles, a study of fundamental interaction that act between them is very important. In nature, there are 4 different types of fundamental interaction. These are gravitational, electromagnetic, weak and strong interaction. According to quantum field theory, all the interactions rely on the mechanism of exchange of quanta. All the interactions are transmitted from one particle to other by successive process of emission, propagation and absorption of such mediators. Strong interaction. This is the strongest force in nature and occurs between nucleons. That is a interaction between a neutron and a proton, or a neutron and a neutron, or a proton and a proton. This is the short range attractive force. Nuclear forces are charge independent and is mediated through exchange of pi mesons, which are the quantum of internuclear field. It has a relative magnitude of strength 10 power 13 times that of weak interaction. The time for the interaction is 10 power minus 23 seconds. It explains strong nuclear interaction between hadrons. Since proton, neutron and pi mesons are thought to be built of more fundamental entities, that is quarks, the strong interaction is believed to be mediated through the exchange of another particle called gluons between the quarks. Neither gluons or quarks have been observed in free state. Next interaction is electromagnetic interaction. It operates on all charged particles. Electromagnetic interactions are charge dependent, whether the charges are attractive or repulsive. The range is infinite and the interaction works through photon. The formation of electron-positron pair from gamma ray is an example of electromagnetic interaction. The third fundamental interaction is weak interaction. It takes place in the nuclear characteristic time 10 power minus 10 seconds. The beta decay of radioactive nuclei and weak decay of strange particles are weak interactions. Weak interaction is a very short range nuclear force and is mediated through bosons. The strength of weak interaction 10 power minus 10 times that of electromagnetic interaction. In weak interaction, parity is not conserved, and this violation of parity distinguishes weak interaction from other fundamental interaction. The important development in the study of this interaction is weak and electromagnetic interaction into the electro-weak interactions. The fourth type of fundamental interaction is gravitational interaction. It is the weakest of all the fundamental interaction that acts between all bodies having mass and is described by long-range inverse square type Newton's law of gravitation. Einstein extended it to describe gravitational interaction in terms of curvature of space. This interaction is believed to be mediated through the quantum of interaction, that is graviton. It is of extreme importance for astronomical bodies in galaxies and on cosmological scale, since large masses and distance are involved in the gravitational interaction. Gravitational interaction, however, becomes inappreciable when the interaction of elementary particles, nuclei and atoms are considered. Today we are diving into the world of quantum numbers. In classifying the various elementary particles, several discrete quantum numbers are used. We are already familiar with two such quantum numbers, namely charge and spin. These quantum numbers specify measurable physical properties and are always conserved. And the other quantum numbers are baryon number, lepton number, strangeness number, hypercharge, isospin quantum numbers. Each baryon is given a baryon number B equal to 1. Each corresponding anti-baryon is given a baryon number B equal to -1. All other particles have B equal to 0. The law of conservation of baryon states that sum of the baryon numbers of all particles after a reaction or decay must be same as the total before. Lepton numbers. Leptons are supposed to possess a property called lepton number, which is represented by capital L. Since the neutrino associated with electrons and with muons are recognized as different, we introduce two lepton numbers Le and L mu, both of which must be conserved separately in particle reaction and decays. The strangeness number. The properties of K meson and hyperons appeared at first to be paradoxical in that they are produced by high energy reaction, but always in pairs. If one particle of some kind is produced them simultaneously, the another different particle is also emitted. This is termed as the associated production of kaons and hyperons, which are known as strange particles. Hypercharge. A quantity called hypercharge, which is conserved in strong interaction. Hypercharge is equal to sum of the strangeness and baryon numbers of the particles, which is represented by y equal to s plus b. Isospin and isospin quantum number. The strong interactions are concerned. The neutron and the proton are two states of equal mass of nucleon doublet. It is found that particles occur in multiplets. For example, singlets, neutral eta mesons, omega hyperons, lambda hyperons, doublet, proton, neutron, triplet for neutral pi mesons, negative and positive pi mesons. Isospin can be represented by a vector I in isospin space, whose component in any specified direction is governed by a quantum number denoted by I3. The possible values of I3 are restricted to plus I to minus I, including 0. If I is half integral for the neutron. Similarly, for the pion triplet, I equal to 1. The charge of meson and baryon is related to its baryon number, the strangeness number, and isospin number component I3. Next, we discuss conservation laws and the symmetry among the elementary particles. A very important set of conservation laws is related to symmetries involving parity, charge conjugation, and time reversal. Conservation of parity. Parity relates to symmetry of the wave function that represents the system. If the wave function is unchanged when the coordinates x, y, z are replaced by -x, -y, -z, then the system has a parity +1. If the wave function has its sign changed when the coordinates are reversed, then the system has a parity -1. Changing the coordinates x, y, z into -x, -y, -z converts a right-handed coordinate system into a left-handed coordinate system. In terms of symmetry, the meaning of conservation of parity is that in any situation where parity is conserved, the description of the reaction will not be changed. In strong nuclear and electromagnetic interactions, parity is conserved, but it is violated in weak interaction. Since parity is conserved in strong electromagnetic interaction, it is a good quantum number, and an energy eigenstate is also eigenstate of parity. Non-conservation of parity in weak interaction leads to a charge conjugation. Charge conjugation is the act of symmetry operation in which every particle in a system is replaced by its antiparticle. If the anti-system or antimatter counterpart exhibits the same physical phenomena, then charge parity is conserved. For example, if in a hydrogen atom the proton is replaced by an antiproton and the electron is replaced by a positron, then its antimatter atom will be behaved like an ordinary atom. If observed by a people also made up of antimatter, in fact, C is not conserved in the weak interaction. Strong and electromagnetic interactions are invariant under charge conjugation operations. Time parity. T describes the behavior of a wave function when T is replaced by minus T. The symmetry operation that corresponds to the conservation of time parity is time reversal. Time reversal symmetry implies that direction of time is not significant. A combined symmetry operation in which antimatter mirror image of a system is done in reverse process. The conservation of CPT means for every process there is an antimatter mirror image that takes place in reverse. The particular symmetry seems to valid for all interaction, even though its component symmetries sometimes fail individually. In summary, studying the elementary particle is essential for deep understanding of the universe, advancing scientific knowledge and technology. Thank you.